So this is the end of our topics for 7.3. We've talked about slicing a solid, and if the slices all have the same shape face and we can write an expression for the area of that face, then we can add up the area times the thickness, which would give the volume of each slice. And then imagine we were adding up infinitely many, infinitely thin slices by using an integral to find the volume of the solid. So the first thing we did in 7.3, slices where the shape was a square or a rectangle, or it could have been a triangle too. The second part, what if we revolve a region about an axis? Then we're going to make a shape that we can slice into disc-shaped slices, and we can find the volume again by adding up infinitely many, infinitely thin slices whose face is a circle. So we end up using the formula for the volume of a cylinder, pi r squared h. And that h ends up being our teeny tiny change in x or teeny tiny change in y, our dx or our dy. So two more things that we need to talk about. What if the axis that we revolve around is not the x-axis or the y-axis? So you watch this here. This is going to be same idea as the last section, the last videos we saw. I have a figure. Here's region R. I'm going to revolve it around the horizontal line y equals 6. So I already have my region shaded in. I'm going to draw in my axis of revolution in red. I'm going to draw the reflection of my region over that axis. So we'll go up here. That's, I don't know, R, right? So you can imagine if you held that red line still and you could twirl this region R around it, we would make a solid. Notice that region R is flush against the axis. So it's gonna be different in the next couple examples. But here we have that same idea. If I took a slice, it would just be a face that's a circle with a thickness. So we call that a disc. I'm going to use the same process I used in the last section. I'm going to start my pen here on the axis of revolution. I'm going to draw in one slice. But remember, I want to draw first toward the curve in the picture that I actually have an equation for. So this here is y equals 4 natural log of 3 minus x. So when I draw my slice, I'm going to draw down toward that boundary first and back up here. So now that green slice, if I draw in the radius, I start my pen at the center of this circle, which is the face of my disc, and draw the radius down to the edge of that circle, right? And what two curves does my blue radius bump up against? Well, its top limit is my axis of revolution, y equals 6, and the bottom of my blue radius hit this curve, y equals 4 natural log of 3 minus x. So can I write an expression for the length of that blue radius? Yeah, because it's a vertical line segment. If I wanted to find its length, I'm going to subtract the top y value minus the bottom y value. Well, the top y value is 6, and the bottom y value comes from this function, 4 natural log of 3 minus x. Now that I know my radius, I can write my integral. I'm going to integrate from, if I'm taking, no, back up one step. If I have an axis of revolution that's horizontal, I have to take my slices perpendicular to it. That means I'm taking vertical slices. It means the thickness of this slice is a very tiny change in x. So I already know I'm going to write my integral with respect to x. My lower limit and my upper limit therefore have to be x values. They're pretty clear in the picture. The shading goes from 0 to 2. And then the volumes I'm going to add up are volumes of cylinders. This is going to be pi r squared, and then dx is my thickness, my height of my cylinder, and my radius I've just figured out. 6 minus 4 natural log 3 minus x. So I didn't specify here, but this is an integral that's complicated enough they would not expect you to integrate this by hand. You might be asked to report the answer. It would be by typing this into your calculator. But this is the integral we're looking for. Final answer. All right, I'm going to use those same steps here. This time I'm going to have to make my own picture. Find the volume of the solid generated by revolving the triangular region bounded by y equals 2x, y equals 0, and x equals 1, about x equals 1. Oops. All right, so I have a graph. I'm going to bound this area by y equals 2x. It's a line with slope 2, contains the origin. The vertical line, x equals 1. The horizontal line, y equals 0, well, that's the x-axis. I'm going to revolve that around the vertical line, x equals 1. So I'm going to start by shading in my region. I'm going to make my axis of revolution equal to, in red here. I'm going to reflect my region about the x-axis. Oh, no, not about the x-axis, about my, whatever my axis of revolution is. So imagine taking that gray shaded triangle and flipping it around the x-axis. So you may have figured out that you would make a cone, and we could find the volume of that cone by using a formula for the volume of a cone. But here we're practicing to make sure that we know how to slice a shape. Maybe it has a volume that doesn't make a shape that we know. So we want to practice this technique so that we can double check, so that we can be prepared to use it for shapes that don't have an easy formula from geometry. All right, so now I'm going to make a slice. I'll use my green pen. I start my slice at the axis of revolution. Notice this time my axis is vertical because I'm going to have to take a horizontal slice. I start my pen at the axis of revolution. I'm going to draw toward the curve I have an equation for, back behind the axis of revolution out to the other side, and back to where I started. So that green slice, it's a circle, but it has a thickness. So I drew it kind of trying to draw it in perspective. The good news is your picture doesn't have to be great for it to still work. All right, so to write my integral, I'm going to need an expression for volume, which is going to be pi times r squared times the thickness of the disk. In this case, since I took my slices horizontally, the thickness is going to be a very small change in y. I'm going to start writing my integral with respect to y. I might even fill in the parts that I know. That's pi. This is going to be radius squared times the thickness. So if I'm integrating with respect to y, these need to be y values. The bottom y value in this picture is the x-axis, which is y equals 0. The top y value is going to be the y-coordinate of that point. Well, it has x-coordinate 1, and this is the graph y equals 2x, so 2 times 1, this is going to be 2. I'm integrating from 0 to 2. Now I have to figure out an expression for my radius. I'm going to use my blue marker. I'm going to start on the axis of revolution at my green slice. I'm going to draw toward the curve whose equation I know. So that little radius, on its right-hand side, let me back up. That radius I drew is a horizontal line segment. And if you need to find the length of a horizontal line segment, you subtract the x-coordinates of the endpoints. Well, the right-hand edge bumped up against my axis of revolution, which has the equation x equals 1. On the left-hand side, I crashed into that linear function, which was y equals 2x. But I don't need an expression for y, I need an expression for x, because I need the x coordinate of that point, so I can subtract from the other x coordinate and get the horizontal distance of that radius. So if y equals 2x, then y over 2 equals x. So my radius, if I want the distance to be positive, I have to subtract the bigger x minus the smaller x. So that's the rightmost x minus the leftmost x. Oops, which I just said was y over 2. So now, if you've gotten it right, and remember that you're going to have to square the radius, it doesn't actually matter if you reverse the order of the subtraction in this case, because even if you reverse the order, you would get a negative distance, but you're going to square it, right? And that's going to sort of wash away that error. It's not a super huge deal. Don't stress over getting the subtraction correct when you're finding a volume in a case where you're going to square the radius. So this is my final answer.